Hello everybody, welcome to Pencil College. In this video we will learn about second derivative and how to use it to actually find the nature of stationary points. So the last chapter 15.1 we actually learn how to find nature of stationary points using first derivative test. So today we're gonna learn how to do it using second derivative test. Okay, so as I've mentioned, today we will learn how to determine whether a stationary point is maximum or minimum point by using second derivative test. Okay, so the types of stationary points we have minima and maxima, minima, and the point of inflection. Okay, so in a in a situation where your second derivative is less than 0, it is actually a maxima. Second derivative more than 0, it is a minima. So very straightforward, you don't need to do the sign test. Okay, so all you need to do is just to do the second derivative, sub in the x coordinate. If it's less than 0, it is a maxima. If you do a second derivative, it's more than 0, it is a minima. Okay, so what if you sub in and you get 0? Okay, then it could be a point of inflection. Okay, but it is not necessarily, okay, a point of inflection. Okay, one of a very good example that we can find is x to the power of 4. Okay, so the graph of x to the power of 4 is actually y equals to x to the power of 4 actually looks like this. Okay, actually looks like this, just like the x square graph, and its second derivative at x equals to 0 is actually 0, but it is actually not a point of inflection. Okay, so for such cases, you have to revert back to your sign test, okay, or your first derivative test. Okay, so remember we actually did this this same question using the first derivative test in the previous video. Okay, so let's find so all we had to do is we had to do dy dx again to get 3x squared plus 12x plus 3. Okay, so let us differentiate this again to find the 2y dx squared. 6x plus 12. Okay, so remember that in the previous video we actually solved this. We actually solved for the stationary point by subbing dy dx equals to 0. Okay, and we got the two different x values, which is let me recall, which is negative 0.268, so negative 0.268, and the other value is negative 3.732. Okay, so now all we have to do is just to take the second derivative, sub the x into the second derivative. Okay, so like for example in this case where x is equals to negative 0.268, so we sub it in, so d2y dx square at x equals to negative 0.268 is equals to let's say a value that is 0.268, so it's probably 1.2. so let's just say this value is approximately 10. Okay, so this value is actually more than 0. Okay, so this says that it's a minimum point. Oops, sorry, just erase this. Okay, and if we were to do the d2y dx square and we sub in the value at x is equals to negative 3.732, then we'll realize that this is probably about 22 minus 22 plus 12. This will be approximately minus 10. Okay, which is definitely less than 0. So this is a maximum point. Okay, so recall that our graph in the previous in the previous video, it looked something like this, right? So this is the point negative 3.732, and this is the point negative 0.268. Okay, so recall that it looks something like this, and really that the second derivative test actually shows that this is a minimum point and this is a maximum point. Okay, so this is proof that the second derivative test works. Okay, so another example to show you how the second derivative test actually fails sometime. So let's say we do a second derivative test for y equals to x cubed. Okay, so let's first find the stationary point. So we take dy dx of x cubed. So this is for the x cubed case, okay, so dy dx will be 3x squared. Okay, so then I get the stationary point at x equals to 0, right? So I take d2y dx squared, and this will be 6x. When I sub in x equals to 0, this will be equals to 0. Okay, so this is not conclusive, so I will probably have to use the first derivative test to solve for it. But in any case, after using the first derivative test, you will find out that this is a point of inflection. So this is how the graph of y equals to x cubed will look like. Okay, so how about y equals to x to the power of 4? Okay, so let's just try this. So similarly, we take dy dx, and we get 4x cubed. Okay, so we solve when this equals to 0, the value of x is 0. Okay, at stationary point. So let's take d2y dx squared, and this is actually 12x squared. Okay, so we sub in this value, x equals to 0, so we have d2y dx squared at x equals to 0. This would be equals to 0. Again, this is not conclusive. Okay, and therefore if we sketch out the graph, it looks something like this. Okay, so y and x. Okay, so in both cases we get zeros, but it is not conclusive enough to say that it is a point of inflection, because there are cases where it's a point of inflection, there are cases where it is just a minimum point. Okay, in the case where you want it to be a maximum point and the second derivative test 0, you just have to put a negative sign here. Okay, so negative x to the power of 4 graph. So this is proof that actually the second derivative test, when you get 0 for it, you have to do the first derivative test. Okay, so it's not conclusive when it's 0. So in summary, we have determined whether a stationary point is a maximum or minimum point by using second derivatives. Okay, we have also learned how the second derivative would behave in a case where there's a minimum, a maximum, or a point of inflection. Okay, so if it's a point of inflection, the second derivative will have to be 0. But when you solve for the second derivative to be equals to 0, it does not necessarily mean that it is a point of inflection. So it's just a necessary but not a sufficient condition. Okay, here are some questions that you can practice on your own. Do try them out. Okay, and lastly, I hope you enjoy this video. For more videos, please visit www.pencilcollege.com. Thank you.